What's outside the universe? What do you think would happen if you could go outside the universe? You might imagine finding just empty space, maybe filled with dark matter, a vacuum, gases, or something like that. But take a moment, sit back, and really think about what could be out there beyond our universe. Is it possible that there are multiple universes, like a multiverse, or is it all just a big, empty space? Theories of quantum foam and cosmic strings suggest our universe might be more complex than we can imagine, and some even propose it's infinite, without any edge at all. It's all quite confusing. Our universe is so huge that it's a 93 billion light-year journey from end to end. And guess what? We've only seen 4% of it, leaving an enormous 96% unexplored and unseen. We've barely scratched the surface of what's visible, and here we're already dreaming about what's outside our known boundaries. Sounds a bit silly, right? However, human curiosity, coupled with our technological advancements, has begun to uncover answers to these questions. This video is going to answer some of your questions, but as a warning to you now, it might actually make you think of even more questions. 26,823 hours were spent working on this video, and I've got to tell you, my head is still spinning from looking into all these wild ideas about what's outside our bubble. Let's start with an obvious concept. Do you remember those moments watching Spider-Man or Doctor Strange, where they talked about bringing people from other universes? Sure, those stories are all make-believe, and we don't have actual superheroes flying around.
But get this.
The idea of a multiverse presented in those movies might not be just a fantasy. Our universe, with all its galaxies, stars, and laws, is just one among an infinite number of universes making up the multiverse. Each of these universes could operate under a completely different set of rules, different physical laws, constants, and dimensions. This isn't just wild speculation. It's a theory at the intersection of cosmology, quantum mechanics, and string theory. But how did we get to thinking about such a wild idea? Well, it all starts with quantum mechanics, and this thing called the many worlds interpretation. Imagine that every choice you've ever made spawns a new universe for each possible outcome. Whether you go left or right, up or down, each decision branches off into its own universe where events unfold in alternative ways. Then there's the theory of cosmic inflation. Cosmic inflation is like the universe got a supercharge right after the Big Bang, expanding faster than the speed of light.
Maybe, just maybe.
Creating pockets of space that ballooned into their own separate universes. Each of these could have totally different laws of nature from what we know. The multiverse isn't the only concept. It's one of many possibilities, and I'm about to discuss the major ones. One major theory we're about to discuss is like a cool puzzle that tries to fit two big science ideas together: quantum mechanics and general relativity. Quantum mechanics is all about tiny particles and their crazy behavior. And general relativity explains how gravity works and how space can bend. String theory suggests that everything in the universe, at its smallest level, is made up of tiny, vibrating strings, instead of just pointy dots. Think of these strings as tiny, stretchy pieces of string that can wiggle in different ways. Each wiggle makes the string act like a different particle, the tiny things that make up everything around us, each having its own mass and charge, kind of like whether it's more positive or negative. According to string theory, the universe is like a huge musical instrument, and these strings play all the notes. String theory is trying to be the bridge between those big science ideas I mentioned earlier, but it also throws in a twist that our world might have more than the usual 3 dimensions of space, plus 1 of time. String theory says there could be up to 11 dimensions, but most of them are super tiny and curled up so we don't notice them. And get this, string theory isn't just one idea, there are a few different versions, like Type 1, Type 2A, and Type 2AB. These versions are like different flavors of the theory, and they all include something called supersymmetry. This is a fancy word for a kind of matching game where particles that spin differently are connected in a special way. So, in the big picture, string theory is trying to tell us that the universe might be way more interesting and complex than we ever thought, with all these tiny strings vibrating to create everything we see, and some things we can't even see because they're in dimensions beyond our normal experience. Imagine, if you will, our universe not merely as a vast expanse of stars and galaxies, but as a 3-dimensional membrane floating within an even larger, higher-dimensional space commonly known as the bulk or hyperspace. This perspective is not just a leap of imagination, but the groundwork of brain cosmology. a theory deeply intertwined with string theory, superstring theory, and M-theory. At the heart of brain cosmology is the notion that our observable universe is actually confined to a brain. This means that while we live, move, and have our being within this three-dimensional brain, there exists around us a bulk, a higher dimensional space that houses our brain among potentially many others. The distinction between the brain and the bulk is crucial. If the extra dimensions that curled up within our universe, then the bulk doesn't need to be referenced explicitly in our day-to-day understanding of physics. However, should some dimensions stretch infinitely into the bulk, it opens up the possibility that other brains, other universes like ours, might be moving through this vast, higher dimensional space. Imagine our universe as a single page in a giant book. Now picture gravity as like a pencil mark that can be drawn not just on our page, but also spread across the other pages in the book. This is why gravity seems weaker to us compared to other forces like magnetism, and the force that holds atoms together, which only draw on our single page. Brain's cosmology suggests our universe, or page, is part of a much bigger book, the bulk, which helps explain some tricky puzzles like why gravity is so light-handed compared to other forces, and why the universe's energy, the dark energy, is less than we might expect. It's all because we're only looking at one page of the whole book. To put these ideas to the test, experiments are currently being designed and conducted. Early models of brain cosmology date back to the 1980s, with researchers proposing a five-dimensional universe where particles are confined to a narrow slice of space-time. Mirab Gogbarashvili's work in the late 90s further cemented the idea, suggesting our universe could be akin to a thin shell or brain expanding within a five-dimensional space, offering solutions to the hierarchy problem. Perhaps one of the most intriguing models arising from brain cosmology is the ekpyrotic model. This model portrays our universe as a three-dimensional brain within a five-dimensional surface. It opens up the possibility that our universe's Big Bang was the result of a collision or interaction with another brain in bulk. Such a scenario not only offers a novel explanation for the origin of our universe, but also for the potential interaction between our universe and others within the bulk. But the plot thickens with the idea of bubble universes. Think of our universe as one bubble in an endless sea of bubbles, each floating in its own vast, expanding space. These bubble universes are born from eternal inflation, a never-ending expansion of space. These phenomena not only exist outside our universe, but in quantities so vast they defy comprehension. It's like inflation hit the pause button in our patch of the cosmos, allowing stars and galaxies to form. But outside our bubble, the expansion party never stopped, popping out new universes all the time. These bubbles are so far apart and expanding away from each other so fast that they'll never bump into each other, because each bubble is isolated in its own island universe, with possibly its own set of natural laws. And when you think the concept of the multiverse ends at bubble universes, the idea of parallel universes takes the stage, at much grandeur level, and it intertwined with the complexities of string theory and quantum mechanics. It states that our universe, immense and governed by precise laws, might merely be one among an array of realities residing in a dimensionality that eludes our perception.
In short,
universes that coexist but don't interact. These parallel universes, nestled in dimensions alien to our three-dimensional experience, operate under principles foreign to our understanding, and remain untouched by our universe in any discernible manner. In these vast expanses, realities diverge dramatically. Some universes could share a resemblance with ours, while others defy our most fundamental physical laws. We're faced with the possibility of universes where the force of gravity behaves unlike anything we know, or where time itself unfolds in reverse. The very essence of what we perceive as reality is put into question, hinting at the existence of domains so strange they surpass our wildest speculations.
Meanwhile,
Quantum mechanics introduces the principle of superposition, revealing a universe where particles can occupy multiple states simultaneously until observed. This phenomenon, scaled to the macro level, intimates a cosmos where entire universes exist in parallel, each charting its unique course through history and evolution. The contemplation that every quantum possibility might manifest as a separate universe in a vast multiverse reshapes our understanding of cause and effect, existence, and the cosmos itself. You might be on board with the whole multiverse idea, but here's another brain twister that some smart scientists out there are chatting about: And that is quantum foam. Again, it sounds like something out of a sci-fi novel, right? Let's break it down into something a bit easier to get our heads around. First off, delve deep into the tiny world of subatomic particles, and things get weird. There's this thing called the uncertainty principle, so it basically says you can't know both where a particle is and how fast it's moving at the same time.
Ernst, are you familiar with Heisenberg's uncertainty principle?
I can't say that I am, Professor.
Well, it states that the more accurately we measure the velocity of a particle, the less accurately we can measure its position in space.
The more you know about one, the less you know about the other. Because of this, space isn't as empty as we thought. It's actually bubbling with energy and particles that pop in and out of existence like magic. This constant buzzing and bubbling is that quantum foam. What's this quantum foam doing beyond the edge of the universe, where we can't even see? Our universe has a sort of boundary, not a physical one, but a limit to what we can observe. Beyond that, it's all guesses and theories. But here's the kicker. Quantum foam is everywhere, filling up every nook and cranny of the cosmos, even the bits we can't see or haven't yet seen. Think of the universe like a room and quantum foam like air. Just because you step outside the room doesn't mean you leave the air behind. It's all around, inside and out. So this idea that quantum foam could be outside the edge of our universe, it's not only possible, but likely because the quantum foam doesn't care about our human-made boundaries. It's part of the fabric of space-time itself everywhere, from the deepest voids between galaxies to the very edges of what we can observe and beyond. Then we have wormholes, often referred to as Einstein-Rosen bridges, stand as one of the most fascinating hypothetical constructs in physics. Picture them as cosmic shortcuts, tunnels through the fabric of space-time, enabling paths that connect distant regions of our universe, or perhaps even doorways to other universes entirely. This notion of wormholes not only captivates our imagination, but also rests on the fringes of theoretical physics, inviting us to ponder the extraordinary possibilities they present. The concept of wormholes finds its roots in Albert Einstein's theory of general relativity. This theory revolutionized our understanding of gravity, depicting it as the curvature of space-time by massive objects, just as a heavy ball placed on a trampoline warps the fabric around it. Celestial bodies like stars and black holes distort the space-time continuum. It's within this complex, warped space-time that the idea of wormholes emerges. They are envisaged as bridges across this curvature, linking disparate points in space-time. At the quantum scale, space-time is far from smooth. It's akin to a turbulent sea, known as quantum foam. As we have already discussed, it's the point where virtual particles flicker in and out of existence. Within this chaotic quantum foam, transient wormholes might spontaneously appear and vanish, much like bubbles in a carbonated drink. These fleeting wormholes add another layer of mystery to the already perplexing nature of quantum physics and general relativity. Don't confuse them with black holes because they exist within the universe, and we are discussing something that might be outside of it. That's the reason a wormhole is thought to have two ends, termed the throat and the mouth. The throat serves as the passage between the mouths, which could exist in entirely different regions of space-time. However, the stability of a wormhole is a major challenge. To prevent it from collapsing under its own gravity, theoretical physics proposes the necessity of exotic matter. This matter, characterized by negative energy density and pressure, would theoretically counterbalance the gravitational forces threatening to shut the wormhole. Yet the existence of such matter remains speculative, as it has never been observed. The traversability of wormholes is another intriguing question. While they tantalize us with the possibilities of crossing vast cosmic distances or even achieving time travel, the reality is more nuanced. Theoretical models suggest that wormholes, if they exist, might be inherently unstable, collapsing the moment they form or if attempted to be used for passage. Overcoming this would require not just exotic matter, but a precise manipulation of the wormhole's properties. The implications of wormholes stretch the imagination. They could offer shortcuts for interstellar or even intergalactic travel, making the vast distances of space more accessible. Furthermore, some theories speculate that wormholes might enable time travel, leveraging the time dilation effects predicted by general relativity. And perhaps most tantalizing of all is the suggestion that wormholes could connect to other universes, offering a bridge to parallel realities. Now, diving into the mysteries that lie outside our universe, We can't overlook one of the oldest cosmic clues we've discovered, the cosmic microwave background radiation, CMB. This ancient echo from the universe's infancy, dating back to about 380,000 years post-Big Bang. Yes, post-Big Bang. Marks a pivotal moment when the cosmos had cooled sufficiently for electrons and protons to join forces and form neutral atoms. This allowed photons, those particles of light, to glide freely across space. The CMB is a stunningly uniform glow across the sky, but dotted with tiny temperature ripples. These minute variations are like the universe's early birthmarks, heralding the clumps of matter that would grow into the vast galaxies and cosmic structures we marvel at today. But here's where it gets even more fascinating. Some forward-thinking theories in cosmology entertain the idea that these ripples in the CMB might whisper secrets of universes beyond our own. Imagine during the universe's dramatic inflation phase, its rapid ballooning right after the Big Bang, that our newborn universe might have felt the gravitational pull of neighboring universes if they were out there. This cosmic nudge from our universe's unseen neighbors could theoretically sculpt distinct patterns in the CMB, akin to cosmic brushstrokes across the early universe's canvas. While these thoughts venture deep into speculative territory, they're stirring discussions and fueling research in the cosmology community, constantly pushing the boundaries of what we know, or think we know, about the cosmos that cradles us. When exploring the era preceding the Big Bang and its remnants that stretch beyond our universe, one might wonder if perfection exists in such realms. The answer is a definitive no. Perfection is an elusive concept, especially in the cosmos. Beyond our galaxy, within and outside the observable universe, imperfections exist, manifestations of the universe's turbulent early stages. Among these are cosmic strings and other topological defects, remnants of the early universe's phase transitions. Cosmic strings, for example, are theoretical constructs believed to be one-dimensional fissures in the fabric of space-time. Formed during the universe's cooling phase, much like how ice crystallizes from water, these entities could span light years while being almost inconceivably thin, at a scale of about 10 to the minus 35th meters. Despite their slender profile, cosmic strings could carry significant mass and energy, exerting a considerable gravitational influence on their surroundings. Their existence could dramatically affect the cosmos's architecture, from galaxy distribution to gravitational wave generation. Topological defects encompass a broader class of phenomena, including cosmic strings, domain walls, and monopoles, each a testament to the universe's asymmetric cooling. Monopoles, for instance, are singular particles proposed to possess a unique magnetic charge, a relic of the decoupling of fundamental forces in the universe's nascent moments. Domain walls, akin to cosmic barriers, might have formed between regions settling into disparate vacuum states during the universe's cooling, each carrying mass and their unique influence on the cosmos's structure. The pursuit of understanding cosmic strings and other topological defects is not just an academic exercise. It offers a window into the laws that dictated the universe's earliest moments. These entities, if they exist and can be detected, could validate current theoretical models, offering insights into cosmic inflation, the anisotropies observed in the cosmic microwave background radiation, and the mechanisms behind large-scale structure formation in the universe. However, direct evidence for these cosmic imperfections remains elusive. Ongoing observational efforts, including the analysis of the cosmic microwave background radiation and gravitational waves, aim to uncover these hidden aspects of the universe's formation. The discovery of such phenomena would not only underscore the theoretical frameworks predicting their existence, but also illuminate the processes shaping the cosmos's very foundation. The conversation about what exists outside our universe often leads to the mention of other forms of intelligence, normally termed aliens. Yet, from a scientific viewpoint, this discourse pivots toward the digital universe theory, also known as the simulation hypothesis. This concept suggests that our universe, in all its detailed complexity, might be an advanced digital simulation created by a superior intelligence or an advanced civilization existing in another dimension. Essentially, this theory speculates that our reality, including the Earth, celestial bodies, and even the fundamental laws governing physics, could all be elements of an elaborate computer program. Don't be astonished yet, I have something more to tell you. Philosophically, this theory traces back to the musings of René Descartes, who doubted the veracity of anything outside one's own consciousness. This line of thought has been extended in contemporary times by thinkers such as Nick Bostrom, who, in 2003, articulated a trilemma suggesting that either advanced civilizations do not survive to develop simulation technologies, choose not to create simulations if they do, or we almost certainly exist within such a simulation. In theoretical physics, particularly through the lens of quantum mechanics, the hypothesis finds fertile ground for speculation. Quantum mechanics introduces phenomena that suggest the physical state of systems might depend on observation, fueling the argument that our perceived reality could be artificially simulated. The implications of the digital universe theory are profound, challenging fundamental beliefs about our reality, the nature of consciousness, and the concept of free will. It posits that if our universe is a simulation, it raises questions about the entities responsible for its creation and their intentions. Many literatures such as Matrix or Goliath have also been produced on this conception. Despite its thought-provoking nature, the simulation hypothesis faces criticism, primarily due to the absence of direct evidence and its unfalsifiability with current scientific methods. This has led some to view it more as a philosophical speculation than a scientific hypothesis. Nonetheless, efforts to find empirical support for the theory have been proposed, including searching for anomalies in physical laws or patterns in cosmic rays that could hint at a simulated reality. Now, telling you a bunch of these things about what could possibly be outside the universe, would you believe me if we say there is nothing at all? Well, it's not just me saying it. Instead, there is a theory named void theory. In the world of cosmology and astrophysics, void theory doesn't point to a singular, well-defined concept. It encapsulates a variety of thoughts concerning the existence and importance of cosmic voids in our universe. Yet if we broaden our perspective on void theory to include philosophical or speculative ideas suggesting the universe is fundamentally empty or meaningless, or as a notion proposing existence springs from non-existence, then we venture into a domain that blends science, philosophy, and metaphysical speculation. In cosmology, voids are identified as massive empty spaces interspersed between filaments in the cosmic web, which is the large-scale structure of the universe. These filaments, laden with galaxies and galaxy clusters, delineate the enormous empty regions known as voids. Spanning hundreds of millions of light years, these voids represent the largest structures in the known universe. Their study sheds light on the universe's grand architecture. The distribution and dimensions of these voids offer insights into dark energy's nature, the enigmatic force behind the universe's accelerated expansion. Dark energy, believed to fill every corner of space, plays a crucial role in the expansion of these voids. Due to their sparse mass, voids are less influenced by gravitational forces, making them expand more rapidly compared to matter-dense regions. Observing this expansion offers a window into dark energy's characteristics. Moreover, voids provide a unique setting for examining gravity and cosmological theories, serving as simplified, well-defined environments for observing phenomena unencumbered by the complex interactions typical in denser cosmic regions. This aids in refining models of cosmic evolution and dark matter distribution. On a more speculative or philosophical level, the existence of these vast cosmic voids stirs contemplations about the nature of the universe and our very existence. They highlight the universe's vast emptiness and the scarcity of matter, prompting existential musings on life and civilization's significance in the grand cosmos. Such reflections hark back to ancient philosophical debates on the concepts of void, existence, and nothingness. Exploring all these cosmic concepts, we still ponder what's truly outside the known universe, like the exact and actual thing. But here's where things take a turn into even more speculation. What if the universe, with all its mysteries of quantum foam, cosmic strings, and potential multiverses, isn't just a series of cosmic Russian dolls, one inside the other? What if, instead of looking for an edge or a boundary, we're actually part of a finite universe that loops back on itself, with no beginning or end as we understand it? This is where Stephen Hawking and James Hartle come in with their no-boundary proposal. Picture the universe not as a never-ending expanse, but more like the surface of the Earth. You can keep going in any direction, but you'll never fall off the edge. You'll eventually end up back where you started. This means there's nothing outside this universe, just we are circling around. This analogy helps us grasp the idea of a universe that's finite in size, but without any boundaries. A closed loop where space and time curve back on themselves. The real mind-bender here is how time itself transforms in this model. At the universe's birth, time wasn't as we know it. Instead of flowing like a river, it was more like a dimension of space. Only as the universe expanded did time begin to tick forward in the way we experience it. This smooth transition from a space-like to a time-like dimension sidesteps the need for a universe-popping singularity at the Big Bang, offering a graceful curve back to a realm we're still struggling to understand. What do you think is outside the universe? Comments are not expected but are always appreciated.